Okie dokie. All right, so hello again. Welcome, welcome. So I'm going to leave this part of the handout like still filled out, but I am going to erase this stuff so we can talk about it. Bam. So basically, what I have written here is the main rules for aromaticity. And before we go into that, I just want to very briefly talk about stability. So this is something that Dr. West also likes to stress. Aromatic compounds are going to be more stable than conjugated compounds, or just like anything that's not aromatic, basically. So having aromaticity gives molecules a lot more stability than what they're expected to have, which is what this second bullet point is really talking about. So he likes to usually bring up an energy diagram, and he'll show you like the expected stability of benzene and then the actual stability of benzene. And the point, like the main takeaway, is that it's a lot more stable than it's thought to be. And the reason I drew this out here is because cyclohexatriene is literally just benzene. That's like the not common name for it. So again, all this question is saying is benzene more or less stable than what it's expected to be? And it is a lot more stable than what it's expected to be. Jeez, I cannot talk today. I'm so sorry. Blah. Okay. And then we also know that anti-aromatic sucks a lot. We don't want to be anti-aromatic. Non-aromatic is whatever. It's kind of in the middle. And then aromatic is super, super, super stable. And if possible, we always want to be aromatic. And we never want to be anti-aromatic. So going on to the actual rules of aromaticity. So in order to be aromatic, it has to follow 4 rules, 3 of which have to do with just the molecule as a whole, and then one of them is all about the number of pi electrons present. So the rules are it has to be cyclic, planar, and fully conjugated. And for planar, we're going to assume everything that's less than 8 members, so any ring smaller than the one I have drawn right there, we're going to assume to be planar. And then anything bigger than that, we have to kind of figure it out based on other clues. And then fully conjugated just means that everything has to be sp2. So we can't have any sp3 present in the molecule. And then last but not least, it's something called Huckel's rule, which is the 4n plus 2 rule. And essentially all this is saying is that in order to be conjugated, there has to be a number of electrons present that is a multiple of 4 plus 2. And that tends to be kind of confusing for students because, like, just the way you have to think about it, like, n is just any real number, and it doesn't depend on, like, the number of double bonds present or anything. So what I usually tell students is, instead of thinking of it as the 2n plus instead of thinking of it as the 4n plus 2 rule, I always just say, think about it in terms of like these values. So 4n plus 2 could be 2, 6, 10, 14, etc. And then for anti-aromatic, the big difference there is literally just the fact that instead of 4n plus 2, you want multiples of 4. I feel like I just said a lot at once, and I don't know if it stuck, but did that sort of kind of make sense? Yes, okay. All right, so then the difference between aromatic and anti-aromatic is literally just the 4n versus 4n plus 2. But then how is non-aromatic different? Well, it's going to be non-aromatic if it breaks any of these rules. So for example, I have written here sp3 atoms. So if you have any sp3 hybridized atoms present, you are breaking the fully conjugated rule. And then, oh, yes, we did lose him. He said his laptop was dying and he was like, or he was on his phone and his phone was dying and he's like locked himself out. So hopefully he will be able to come back soon. He seemed to be struggling. But yes, okay. I'll keep an eye out for him. I know. Today feels like it's been a rough day for everyone. But yes, okay. So I'm also in that kind of mood today where if I get distracted, I'm just gonna go with it. Like so I want to stay on track so I don't waste your guys' time. But if you like want to talk about anything, like I'm not gonna stop you, kind of thing. I don't know. I don't know what I'm saying. All right. So we talked about aromatic, anti-aromatic, and now we're talking about non-aromatic. So sp3 always means non-aromatic. Also, anything that's 8 or more members, we can talk about it being non-planar. And I'll show you an example because it's easier to do an example than to talk about it like conceptually. But essentially, anything greater than 8 members can either choose to stay on the plane or choose to bend off of the plane and be non-aromatic. And the last thing that's kind of easy to tell when you look at a molecule is radicals. So if you have an odd number of radicals present, you know that you're going to be non-aromatic because you're going to have an odd number of electrons present. Because remember, radicals just represent one single electron. All right. Any questions on what we talked about so far? Okay. Coolio. So the molecular orbital theory we'll talk about after we do the examples, just because it's one of those like weird concepts. Okay. So the other thing I'll show you, just because I already have it written out, are the heteroatom rules. So the heteroatom rules are essentially here to tell us how the heteroatoms are going to behave. So if we have a single bonded heteroatom, that heteroatom is able to choose between being sp2 or sp3. And if it's sp2, we're automatically going to have non-aromatic. But if it's if it's sp3, we're automatically going to have non-aromatic. If it's sp2, we have to figure out how many electrons it's going to donate. And so any heteroatom can donate up to 2 pi electrons. So we can only donate up to 1 lone pair. We can't donate any more than that. So an example of this would be this guy. So oxygen here can choose to be sp2 or sp3. We know that if it's sp3, this will be non-aromatic. But if it's sp2, we have to do some counting. So like I just told you guys, sp2 donates up to 2 electrons. So this extra lone pair is just here to trick you. So I'm going to cross it out. All right, so if it's sp2, it's going to donate those 2 pi electrons. So we get a total of 2, 4 pi electrons. Does this follow the 4n rule or the 4n plus 2 rule? 4N, exactly. So this ends up actually being anti-aromatic if it's sp2. So between anti-aromatic and non-aromatic, what is more stable? Aromatic. Well, yes, aromatic is the most stable, but between the options that we have right now, it's between non-aromatic and anti-aromatic, so we're actually going to pick this guy. And yeah, you were right. I just didn't phrase my question very well. Okay, so any questions about what I did or why I did it for this example? No? Okay. Lauren, are you good so far? Do not apologize. So, basically, the reason it would be non-aromatic is because if we go up here, the criteria to be non-aromatic is to break any of these rules, right? And the rules are it has to be fully conjugated, which is all sp2. So if we ever have anything sp3 hybridized, it automatically has to be non-aromatic. So if oxygen chooses to be sp3 hybridized, that means that it has to be non-aromatic. And then between sp2 and sp3, we decided that being sp2 would become anti-aromatic because of the number of electrons present. And we know that non-aromatic is better than anti-aromatic. So that's why we chose to be sp3 and non-aromatic instead of being sp2 and being anti-aromatic. I feel like I said the word aromatic 100 times. Was that a little bit, did that make it a little bit more clear for you? Good, okay, cool. So the next thing I want to talk about was like the asterisk for the rule that we just mentioned. So in case you didn't get a chance to look at it or write it down, the rule is that boron is an exception to the first rule because it is always going to be sp2, but it is going to donate 0 electrons. So it does not have a lone pair to donate. An example of that would be this one. Sorry that it's like shaking back and forth. So boron, we said that it must be sp2 and it has 0 electrons. So the only electrons we're going to count are the ones from the double bond, which, if you remember, each double bond donates 2 electrons. So here we would have a total of 2 pi electrons. Do you guys remember which rule, 4n or 4n plus 2, does this fall under? Four n plus 2, exactly. So this guy is going to be aromatic. How are we feeling about this one? Any questions? All right. If you guys have any questions at any point, you can, either unmute or just type it in the chat. But I will go on to the next rule. So double bonded heteroatoms, we can either have it double bonded inside the ring or outside of the ring. And if it's double bonded inside the ring, you can essentially just treat it as if it was a regular old carbon, because it's going to be sp2 and it donates one electron, one single electron, not a pair. And if it's double bonded outside of the ring, if it's double bonded outside of the ring, that means that it is going to be sp2, but it's going to donate 0 electrons. And we can look at, yes, someone unmuted for a second. Maybe I'm hearing things. That's okay. So, let's do some examples. Let's start with this one, because why not? So this is an example of being double bonded outside of the ring. So this carbon right here is going to be sp2, and it has 0 pi electrons. So again, if we count up our electrons, how many do we have? We have 2. Cool. So that would make it what? Aromatic, anti-aromatic, or non-aromatic? Aromatic. Perfect. All right, so I'll give you a minute if you have any questions, or if you want to write it, like, take your time to write it down. And then we can do some more examples. Ignore my family and my bird screaming in the background, please. All right, so the next one that we're going to do is similar. We're going to, oh, where'd it go? There it is. All right, so for this one, we're going to draw it out a little bit differently for a moment. Ta-da. All right. So when I draw this out, I'm going to be trying to draw it in 3D, but I might fail at that. Okay, so this nitrogen right here is double bonded to the carbon, and it's double bonded inside the ring. So what we have to realize here is that this one is stuck, right? It's stuck with this p orbital being locked with this p orbital, and they have that double bond between them. So this is just like if we had a carbon that was double bonded, because it's only able to donate this one single electron that's already part of the double bond. So it's going to have another lone pair, but that other lone pair is now pointing on a completely different plane, so it cannot use that lone pair of electrons. That's not available. So instead, when we count the electrons, we have to say, first of all, this must be sp2. It doesn't get to decide. And in total, we have 1, 2, 3, 4 pi electrons. And that would make it what? Aromatic or anti-aromatic? Anti-aromatic. Cool. Ow. Any questions so far? While you guys write this down, I'm going to turn my camera off right quick, but I'm still here. All right, I have returned. I don't see any questions, so I'm gonna assume we're good to move on, unless Anthony, question.
Rosemary, could I see the rules again, please?
Yes, the heteroatom rules or the just the regular ones.
The ones that did like the 2, 6, 10, 14, 18.
Yes.
And so I'm trying to. So in number 14 in the assessment was extra questions that Wes gave us. He said that this 16 annuales is not
Mhm.
aromatic. It has 16, and I thought it would be anti-aromatic.
Ah, sorry. Wait, can you show me or read to me like what the question asked?
Yes. It says, for each molecule below, predict whether the molecule would be expected to show aromatic character or not. Explain your answer in each case.
Okay, so that's the thing. It's not saying which one of these is non-aromatic, right? It's just
Right.
saying which of them is not aromatic. So
Okay.
the other answer choices were all like 4n plus 2, I'm guessing. And that one is anti-aromatic. And you're right, so it is anti-aromatic. The question makes it sound like you're talking about which one is non-aromatic, but they're asking for anything that is not strictly just aromatic. Does that
Right.
make sense? So it's a wording thing.
Okay. Thank you.
Yeah, that's something really annoying. That's the biggest thing about this chapter. Like, I think the material for this chapter is not necessarily like super difficult. It's just the fact that some questions are worded like that, where it's like, oh, pick the one that's not aromatic, and it's like, well, hmm, like what do you mean by that? So you have to read it very carefully. Again, my bird is having a blast. I don't know what she's yelling at, but I promise I'm not torturing anyone. Alrighty. So the next one I wanted to do is this one. All right. So this guy has a double bonded heteroatom outside of the ring. So let me know. What should I do? How should I think about this? What should I think about this? Okay. Yeah, so make sure everything is sp2. Cool. Um this guy we know has to be sp2 because it's double bonded and it gives 0 electrons. And then everything else in the ring is also fully conjugated, so we're good on that front. Next. Good question. So the oxygen in this case is not donating any electrons, and the reason is resonance goes that way up towards the electron. Uh, excuse me, up towards the oxygen. So the electrons are only moving up towards the oxygen. They're never going to go down into the ring. Um, so as Anthony said, yes, there's 2, 4, 6 pi electrons if we don't count any from that oxygen. So this is in fact aromatic. Sort of kind of making sense. Cool, cool. And let's do the one next door. So, boron. Do we get to pick between sp2 and sp3? No, exactly. So it's stuck being sp2, and it donates 0 electrons. So, wait a second. These two are pretty much the same exact thing. This is a boron, this is a double bonded oxygen, so obviously they look different. But functionally, when we're talking about aromaticity, we can pretty much say they're the same. This also has 6 pi electrons, so therefore that one is also aromatic. Woohoo. All right, any questions about the one we just did? Or I guess more so like how they're pretty much the same thing.
Could you tell us which analyses will be on the exam? Or would you happen to know which one he would like to use?
Which what?
Those annules, the ones on the bottom that look across.
Oh, these ones?
Yeah.
So, okay, there's two types of questions that he could ask you. One is he could say, oh, is this aromatic, anti-aromatic, or not aromatic? Or he can ask you a question that's like, which of the following is an aromatic annuline, right? And that will be like written out answer choices. So it'll be like 10, 16, 12, 14, etc., whatever. And so if he asks you like that, you're just picking out which number follows which rule, right? So this guy, is that 4n or 4n plus 2? Cool, so that's aromatic. How about this one? Yeah, so that's anti. This one. And this one. Cool. So if he asks you with the numbers, it could really be any numbers, and you have to just say, oh, is that a multiple of 4 or is it a multiple of 4 plus 2? And then as far as like visually, which one we're talking about, it'll be these two pretty much. It won't get any bigger than that if he shows you a picture. So if we have this annuline, right? How many pi electrons do we have? $14. Oops, I said 14 and I wrote 16. So 14 pi electrons, which rule does that follow? Aromatic or anti? Aromatic, cool. So that one is aromatic. So that's how you kind of go through these kind of questions. All right, so I'm going to go back down here for a second, unless you guys want me to go back up. I didn't ask before I moved on, but okay. So when you have multiple heteroatoms, there we go. So when you have multiple there we go. When you have multiple heteroatoms, I'm saying for the 8th time, they could either be both single bonded, or you could have one single bonded and one double bonded, and you will actually have to like know the difference between those two. So if you have multiple single bonded heteroatoms, you must know that they must have the same hybridization. So they're either both sp2 or both sp3. You can't have just one sp2 and one sp3. And if they are both sp2, each of them are going to donate 2 electrons. And if they are sp3, then they're going to donate 0 electrons. However, if you have one that's single bonded and one that's double bonded, now that double bonded one has to be sp2, right? And so the single bonded one does not have to be the same hybridization. It can pick whatever is more favorable. So they only have to have the same hybridization if they're both single bonded. And then I have some examples, so I'll give you a second to write this down, and then we can do the examples. All right, so let's do this one first. Alrighty then. This guy. I don't know why I put an arrow to it. I'm sorry, I didn't mean to do that. This oxygen. How many max electrons can it donate? So it can donate a maximum of 2, so I'm going to cross out that second lone pair. And same thing for the other oxygen. Cool. So the next thing I would think to myself is, all right, sp2 versus sp3. If it's sp3, what is the hybridization? I mean, what is the label? Like the name, what would we call it? So I'll repeat that. So if the oxygens are sp3 hybridized, yes, it would be automatically non-aromatic. Coolio. So now if they're sp2, each one is going to donate 2 electrons. So we would have a total of 2, 4, 6. Sorry, this was lagging a lot. 2, 4, 6, 8. I'm so sorry about the lag. Hopefully it still makes sense what I'm counting. So 8 pi electrons. So 8 pi electrons. Is that aromatic or anti-aromatic? Anti. Awesome. So between these two, what's more stable? Yes, non-aromatic is more stable. So both of these oxygens are going to be sp3 hybridized, and neither of them are donating any electrons. Any questions?
Rosemary?
Yes.
So in one of these questions, it was using the term reactivity, and it was to say that to have aromatic reactivity. So is that another way he can um, make a question just using that term reactivity?
What exactly did the question say, if you don't mind?
It says, what reactivity do you predict for sulfathiazole?
And then it's asking you like anti-aromatic, aromatic, or non-aromatic?
Yeah, but it's just that word reactivity is new to me.
Yeah. Yeah, that's a really weird word to use for like this type of question, but I guess yeah, it's just asking for the same thing.
No, it's okay. Don't worry about it.
Oh, hello. Sigh. Yeah, me too. Welcome back.
Welcome back, Kareem. We all missed you here.
Thanks.
Yes, we did.
Yeah, here, watch this.
Did we do 11 and 12?
Damn.
Those were my problems, and I wanted to go over it. So it would suck if we did it already.
Yeah, we did
No.
it all. Sorry.
Oh, you're right. Um, sorry. Okay. What was I saying? See, it's one of those days, dude. Literally got distracted for 0.5 seconds, and now I have no idea where I am. No, we did not do that. We waited just for you. Heart, heart.
Oh, thank you.
You're welcome.
Yeah.
All right. Do. Someone signed up for the 7 o'clock session like 5 minutes ago, and I don't know how they did that,
What's the
but
person's name? Is that confidential?
I don't know. I don't even know who it is, to be completely honest. It just started with a G because that's what their email started with.
Oh.
Yeah. Yeah. I don't know how to pronounce that. It's not Gabby, which is who I got an email about, which is weird. Whatever. I just had to send her the email. That's why I disappeared for a second. But so let me close that and we can back to it. Okay, all right. So a question from Lauren was, if neither of the oxygens donate electrons, then is it... Oh, okay, then isn't it anti-aromatic? All right, so great question. The answer is no, because if it's sp3, remember, it's automatically anti-aromatic. So we don't even get to count how many electrons we have. Nothing matters. The fact that it's not completely conjugated means that it's non-aromatic, which is a weird rule, but does that sort of kind of make sense? If we have sp3 or we have non-planar, things like that, it is automatically non-aromatic. Okay, let's do this one. So now there's 3 heteroatoms, which is ugly, but actually, before we do that one, I never did these simple ones. So let's super quickly talk about it. So this first one has an sp3 carbon. So that sp3 carbon automatically tells us it's non-aromatic. The next one in line is a positive charge. So positive charges, negative charges, and radicals are all going to be sp2. And the carbocation has an empty p orbital, so it has 0 electrons. So then we end up having just 2 pi electrons. And that is aromatic. And then if we have a negative charge, this has 2 pi electrons, which is why it's negative. Circle that. And that means we have a total of 4 pi electrons, which would be anti-aromatic. Are these ones okay? I went through them super fast, but how does that feel? Okay, I got one good. So the reason I brought that up is because something that I like to do to make this a little bit easier is okay, or maybe not. Every time I see a ketone, before I do that, that's a great question. So let's say we had a radical the radical just has one single electron. So if we drew it out like this, bam, 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 the double bond would be like this. And then the radical would have one single electron by itself. So we would have 3 pi electrons. And anytime we see an odd number of radicals, we can automatically say that's non-aromatic because it has an odd number of electrons. Make sense? Cool. All right. So anytime I see something big and complicated, I want to simple it down as much as I can. Simple it down? Break it down? So this thing, I'm just going to get rid of it, and I'm going to put a plus charge there, because this is essentially acting like a carbocation. sp2 and 0 electrons. Does that make sense? How / why I did that? Okay. So now, for the S and the O, we have to figure out, are they going to be sp2 or sp3? So if it's sp2 or sp3, we know that sp3 has to be non-aromatic. I'm not even going to ask you anymore. But if you guys look at this, if it's sp2, each one can donate up to 1 lone pair. So I'll draw 1 lone pair for each of them. So if they are sp2, how many pi electrons would we have? Yes. So it would be 8 pi electrons, which would be anti-aromatic or aromatic? Anti, cool. So between these two options, which one do we want to pick? Non-aromatic, yes. So this one seems like a more stable, better deal. How we feel.
Rosemary,
Yes.
could you do number 20 from the chapter 14 problems?
Yes. I just want to make sure everyone's good with this, and then we can go into the practice problems.
Okay.
Everyone good before we move on? Okay. So let's move it on over. I just had them. There we go. Actually, these are my practice problems. Let me see if I have it. I don't. Okay. Give me 1 moment to download them.
Who's Momo?
Nobody. I can't with you guys. I know. I have really weird names for everyone. It might be whatever. So anyway, which one did you want to go over?
20. Don't worry, I call him Henry, so.
Yeah, 20.
Oh, that's really, really funny. Okay. I
Uncle
love
Wes
that
probably
joke because
loves
it
this
just
one.
went on for so long, and now it just the guy at the boba place calls him Ben, and I'm like, I don't know where you got that from, but okay. Um,
I'm dying.
okay. All right. All right. Yeah. Okay.
It is just 14.
I don't
Well, it says drawing the protons.
I know, I hate this one.
okay, so the thing here is this one is one of those questions that is not going to show up on your exam, and I can explain it to you, but I feel like explaining it might do more harm than good because I'm 99% sure he didn't even mention this in class unless it was one of those days that I missed. But essentially, what's happening is some of the protons are pointing out and some of them are pointing in. And the basic summary here is that there's going to be an electron current that's going to be made. Did he talk at all about electron currents?
I don't remember.
Okay, so that probably means he didn't. But essentially, we're going to create two currents, one above and one below. That does not look like above and below, but it's fine. More like above and below. And so some of these protons are going to be like right in the current. So they're going to be like constantly in a field of electrons, whereas some of these are pointed away from the current, so they're never going to be in the field of electron density. So the ones that are pointing towards the field are going to be essentially at 0 ppm, and the ones pointing away from the field are going to be like way higher, like 8-ish or so. Is that an okay enough explanation? Because I don't want to go way over what he did in class.
Yeah, that's fine.
Okay.
Could we do 11,
Cool.
12? For,
Yes. Any other questions from this handout? Or actually, I promised Anthony right quick that I would tell you about some of these naming things. So, okay. I'm going to make my own page because... So the ones that you have to know the common names for, we have toluene, aka methyl. Oh, I made up my own spelling. Methylbenzene. And then we have xylene. Which is dimethylbenzene. And no, they do not have to be ortho to one another. They could be anything, ortho, meta, or para, as long as there's two methyls on the same ring. And then we have something called aminobenzene. And the common name is aniline. And then we have OCH3. And does anyone know what the like IUPAC name for this would be before I give it to you?
methoxybenzene.
Yeah. methoxybenzene. And the common name is nope, I spelled it wrong. Anisole. So, and then also, I'm pretty sure you all know this by now because he's been talking about it for a while. But an alcohol would be phenol or benzyl, or blah, I'm sorry, phenyl, alcohol, or he could say hydroxybenzene. He likes to put that one on there to trick people. And then this one doesn't really have a common name, but if any of the halogens are on there, it'll be either bromobenzene or chlorobenzene or fluorobenzene, so on and so forth. How do we feel about these guys? Okay-ish?
We're good.
Cool. All right. Now we can go back to chapters 11 and 12. Unless we have any more questions here before I switch handouts. All right. Chill. No, chill. Okay. So I'm just going to erase this because this is what we did in tutoring, but it was kind of a hot mess, so I'm just going to erase, erase, erase. All right. Where do you want to start? Just at the top of what you guys... Sorry, go ahead.
I wanted to do questions from the practice problem.
Even better. Okay. In that case, I'm just gonna re-download. Oopsie. I stopped sharing. Give me a moment, I'll reshare. But I'm gonna get a clean copy of the 11 and 12 practice problems because I don't want to go through and erase it. I feel like that'll just take up more time. 11 and 12. Cool. Come on, bro. Share, please. All right. So we're just gonna create a new note. Swaggy. All right. So I'm gonna have you guys tell me what you think. Actually, do you guys want to tell me what you think first and then I show you how I would go through it? Or do you want me to show you first and then you ask questions?
That one is number 3.
Oh my God.
Okay. Cool.
Anthony is
That was fast.
he studied the answers to these things.
He was just like, I don't have time for any of you people. I've done this 100 times. Let's go.
I'm afraid of that guy.
I mean, you're not wrong. It is number 3, but how did you get to that answer?
So you do Grignard's reaction. Then after Grignard's reaction, you do breaking of the epoxides. And then after breaking epoxides, you do protonation.
Cool. Okay, so the first thing you said was Grignard, and anytime we see MgBr or Mg, we know it's Grignard. Cool. And why in this case does, like, we didn't add anything for the Grignard? How come?
Oh, because I was actually thinking of you one day because I read the book for the first time in a while, and it said that because there's a hydrogen there, we cannot add like CH3, CH2 to that. We have to remove that hydrogen.
Exactly. Cool. Okay. So yes, this is an acidic hydrogen. So you're absolutely right. Instead of using this as a nucleophile and attacking here, we actually have to use it as a base, and we just steal this hydrogen, which would give us this. And then, as Anthony kind of said already, we're just going to use that to attack the epoxide and open it up. And then the last step will be to protonate. So does it matter which side of the epoxide we attack?
Oh, you just asked the question just now? Or you made a
Yes.
statement? Okay. No, it doesn't matter.
No, it doesn't matter. Okay, yes. So, it doesn't matter which side you attack because it's exactly the same on each side, as long as you keep track of how many carbons there are. So you eventually are going to add, sorry, let me draw this and then talk so I'm not doing a million things at the same time. So we're going to attack one side and open it up. So we add 1 carbon, 2 carbons, and whichever carbon is not, whichever carbon we didn't attack is the one that has the O minus on it. And then once we protonate, we get carbon 1, carbon 2, OH. And as Anthony said earlier, 3 is the correct answer. So how I would have gone about it, well, it was pretty much, what Anthony said. He did a really good job of like highlighting the main steps. So when I look at this, I would think of those steps, and instead of necessarily drawing it out, like if you want to save some time, what I would do is 1, what the heck is that? Right? Like, how in the world did we add this and then stick that on the end of it? Right? It makes no sense. So because of this group, I would immediately throw that one out. And it's the same thing here. That OCH3, why did we make an ether? Get rid of it. And then here is another ether. Doesn't make any sense. Get rid of it. And then this one doesn't have an oxygen whatsoever, so I get rid of it. And you may not see this. I've been looking at this for like 2 years now, so I kind of just see things. So if you don't see that, drawing it out is completely fine. But if you're able to look at this and through the steps we talked about, realize, okay, it's an epoxide and an acid, which means it's going to be protonated. So I'm going to have an alcohol at the end. If you just know that you're making an alcohol at the end, it makes it really easy to find the answer. Does anything I just said make any sense? I feel like I started blabbering. Okay, good.
Me and somebody
Cool.
were looking at this yesterday. We looked at it for half an hour and we still did not get it.
Oh no, well I'm glad it makes sense now. What part were you guys like stuck on?
Um, so we didn't know that, of course, the acidic hydrogen would react with the Grignard. So we stuck the Grignard, the CH3, CH2 on there. We're like, what's happening? Yeah.
It's that acidity thing, that darn acidic proton. Okay. Doo, 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 doo. I have no idea what that word means. But we can definitely do number 40. Ah, okay.
Are
Fine.
we gonna
Let's do this
even
one.
get mesylate and tosylate? Probably not.
Probably not, but let me just look. Because if it's on this summary they gave us, it's fair game. Yeah, it is on the summary, unfortunately. So it's possible. There is a lot of content on this exam, and he did test you on protecting groups, so I don't know that it makes sense for him to do it again. Yeah. It doesn't make sense, but again, I'm not Dr. West or Dr. Roche, so they like to do a lot of things that don't make sense. So I'm just gonna say probably not, but this is a good question. Any idea about anything about this question? Like, what would you guys think if you saw this right now?
So, Rosemary, I looked in a book and I could not find this thing here. I was like, what is CH3SO2FCO?
That's tosylate,
Okay,
right? Wait, that's
close,
mesylate?
not tosylate. Yes, it's mesylate. So this looks like this: CH3SOOCl. And remember, once we attach this onto here, we would get CHO, S, and then CH3, C2H5. Does that make more sense, Anthony? I feel like this was something that was driving you crazy.
Oh, because it's in condensed formula.
Yes.
All right, I'm gonna write that down.
All right. So once we get to that point, what is this second step going on?
That looks like a carboxylic acid. The what do you call those? The conjugate base of a carboxylic acid.
I don't know that it has a specific name. I could just be making that up. Probably a carboxylate.
Carboxylate. Yeah.
Probably. Yeah. But yes, okay. So more importantly, does it really matter what exactly that group is?
No.
What's it gonna act like?
A base.
Or
Nucleophile?
nucleophile. So the reason it's gonna be a nucleophile is because there isn't really any acidic protons here for it to take. Instead, it'll be a nucleophile and it'll attack here and it'll do an SN2 reaction. So, what's going to happen to the stereochemistry?
It's gonna flip to. It's gonna flip.
It's going to flip, exactly. So, in this kind of like format, the way we represent flipping stereochemistry is by flipping the sides. So we're going to add CH3CO2 here. H will go here, and then we have CH3, C, 2H5.
That's I. Wait.
Mm-hmm.
Yeah. Okay.
Oh, I highlighted the wrong thing. Ta-da!
Okay. Can we go back to 2?
Yes. This is okay before we come back.
Yeah, thank you.
Okay. So let's jump back up. Your interactions between the two of you is so funny. It's my favorite. It's like not supposed to be shady, but like it has the shady undertones. I love it.
We could skip
All
this,
right.
right? We could skip Grenier.
I mean, it's not like an absurd one. You could get something like this.
If you see me crying after the exam, mind your business.
Dude, I don't judge anyone for crying. I went out of my Orgo 2 final bawling my eyes out. Like when I tell you to this day, Dr. West makes fun of me, like in front of his lecture, like his classes. Like he'll be like, yeah, the final is stressful. Like I've had some students who cry during the final, and then he looks at me and I'm like, yeah, what about it? What about it? But yeah, I don't judge anyone for crying. It happens.
Okay. Mm.
Anywho's, 1, 2, 3, 4, 5, 6. But it's so funny. This is wildly off topic, but other students know you as the smart kid.
Ooh.
And I was talking to someone and they were like, yeah, I did so bad on the first exam. And I was talking to the smart kid and I was like, which smart kid? And they were like, you know, Kareem, the tall guy. I was like, oh, yeah, I thank you.
The
I know.
smart
I know
kid?
who that is.
Yeah, even in Orgo Lab, Melanie was like, "Oh, Kareem is so smart."
Yeah, the smart tall guy. That's you.
I
And they were
barely
like,
passed the
yeah,
first one.
you did not barely pass. They were literally like, yeah, we were complaining about our grades, and he was like, I know I did so bad. I got a B. And they were like, I would be so happy with my life if I got a B. And I was like, God damn.
I got a C.
Yeah, you gotta
Oh,
see.
either way, that's still above average.
Oh my
And the
god.
way
So,
you tried it, like, he did not get a B. Like, calm down.
Rosemary, when it comes to mesylate and tosylates, they're always attacking an alcohol.
So the alcohol is attacking them, but they're going to add to an alcohol, yes.
But is the mesylate a nucleophile?
No.
Ouch. Okay.
I mean, okay, you don't have to know the arrow mechanism, but I'm pretty sure the oxygen is the nucleophile and it attacks the tosylate.
Okay, okay.
I'm like almost positive. Now. Okay. So 2-phenyl, 2-hexanol, that's what I was drawing for you guys, and then I got distracted. 1,2-phenyl. I don't know why I chose to draw that benzene in the most awkward way possible, but that's like the best benzene I've drawn, so it's fine. OH. Okay, so how would we make this through the Grignard synthesis? So this is one of those questions that looks really bad, but it's not that bad once you like get into it. So we know that in a Grignard reaction, we're going to end with an OH, and that OH came from some kind of carbonyl. So this indicates retrosynthesis. So I know that I had some kind of carbonyl here, and there was at least one R group on it. And here we have 1, 2, 3 unique groups. So since we have 3 unique R groups, that means that this ketone, this carbonyl had to be a ketone with 2 unique groups. If it was an aldehyde, one of these would be an H. And if this was like an ester or a carboxylic acid or something, one of these guys would be duplicates. You couldn't have 3 identical groups. Does that make sense what I said?
Say it again.
Why? Yes. So basically, in a Grignard reaction, if we have a leaving group, the Grignard is going to add twice, right? So if this was an ester or something, and we reacted twice, 2 of these groups would have to be the same. And since none of them are the same, they're 3 unique groups, that means that there had to be 2 unique groups already on the ketone, and then one of these was the Grignard reagent.
Okay, got it.
Okay, and then hello, welcome to the new person who just joined. We're just going through some chapter 11 and 12 practice problems.
Was that the name that you were being secretive about?
Maybe. Look, I have to get my what's it called? No brain. It starts with a C.
Child?
Confidentiality. Have to have some
Oh.
kind of. Did you say child? This is my child, guys.
Rosemary,
Yes.
so I know we finished number 40, but I was redoing it again. And which are the ones that does inversion? Because I thought like when we do SN2, it gets inversion, right?
Yes. Okay. So let's finish this question and then go back to that one because
Okay.
I want to give you a good explanation. Yeah. Okay. Cool. So we have to react a ketone that has 2 different groups with some R group with a negative charge because that's essentially what the Grignard will be, right? So we're going to look at these answer choices and see which one kind of matches up with our groups. So here we have a 1, 2, 3, 4 carbon chain. 1, 2, 3, 4. 1, 2, 3, 4. Yes, okay, cool. 4 carbon chain plus this guy. So we have this group present, we have this group present, we have this group present, and we know that the OH comes from this part. Why'd I do 2 red? My bad. So this could make that product. Cool. Now, number 2, we have a branched chain. And then we have the same thing as before. So we have 3 of those groups present, but could the Grignard they gave us possibly produce the answer that they told us they wanted?
No.
Exactly. So this cannot work. And this last one, they give you 1, 2, 3, 4, 1 plus this. So are all the groups present here? And I lied to you. I forgot a carbon at the end. I'm so sorry. Are all of the groups present here? Are all of the groups present here?
Yes. Where'd the bromine go?
The bromine is just like a. This is gonna turn into the Grignard, so I just cross that off and make it into a minus.
Okay.
So the
Question?
answer would be sorry, I didn't mean to turn into a demon for a second there, and that really caught me off guard. Go ahead.
Rosemary,
Yes.
what would the Grignard be? As in, like, for this problem, like, I understand what the 2-phenyl 2-hexanol be, but what would the Grignard be?
So the Grignard would be whatever is here that has the negative charge. So it could be either of these groups. That's why the answer would be E. It can't be this one because this is branched and it wouldn't make this. Does that make sense-ish?
Kinda.
Okay. So yeah, I would recommend looking at it like this, like putting it into 4 different pieces and then working backwards and making sure like it has the pieces. But whichever side here has the BR, that's going to turn into the Grignard reagent. So the BR means that that's the Grignard reagent. That's the Grignard reagent. That's the Grignard reagent.
So, question, why did you scribble out that thing on C?
So when we're talking about the Grignard reagent, essentially what we're going to do is knock off the BR and give it a negative charge. That's the only reason I scribbled it, or in the other examples I circled it. So we're just going to get rid of the BR and put a negative charge. Make sense-ish?
So would that make the hexagon that would be the what's it called here, the cycle
Benz?
hexane, right?
Yes, so that would be this. Ta-da.
So now it becomes negative, okay. And that becomes what, the nucleophile?
Mm-hmm.
Okay, and then that big structure next to it, is that the 2-phenyl 2-hexanol or
This is the 2-phenyl 2-hexanol. This is going to be the ketone here that's drawn out. And so when these two react with one another, they make this.
okay.
Okay.
That helped.
Let's zoom right quick back down here. All right. So the question that Anthony asked earlier was, what's going to flip the stereochemistry? What's going to maintain the stereochemistry? Kind of what's going on with that. So SN2 is going to flip the stereochemistry. And we know that PBr3 is an SN2 reaction. So if we had PBr3 here, it would flip in the first step, and then it would flip again in the second step. But mesylate and tosylate maintain the stereochemistry in the first step. So in the first step, it stays the same, and in the second step, it switches. So we get an overall flip in stereochemistry. And that's going to be the same for mesylate and tosylate. And then if we had PBr3 or anything from that list that I said reacts the same way as PBr3, all of those will flip in the first step, flip again in the second step, and so it becomes overall maintaining stereochemistry.
Rosemary?
Yes.
Okay, so I guess the way to remember it would be like top and bottom would flip, and then the others would stay the same. Or the left and right would stay.
So these two we flip, those two stay the same.
Say it again. Point to the ones you said.
This one and this one stay the same, so up and down stays the same. Left and right, the two wedges, that's what flips.
Or we just switch them? We switch them on the sides.
Yeah, we switch the sides. So the H just flips over here.
Still trying to figure out like why did you say it was SN2?
Because we're gonna use O tosylate, so the group that I drew right here. That's gonna be a leaving group. And this is going to be a nucleophile. and that's going to react as an SN2 mechanism because it's going to attack and kick off the leaving group in one step.
So the one we did on the left was a mesylate, and then the one on the right is a tosylate?
No, this would be a mesylate, and this would be just kicking that off and putting a new nucleophile there.
Okay.
Rose, when you're finished with this one, can you do four?
Yes.
Okay.
Okay, so I know this type of projection can be hard to like see and kind of make sense of. But is that like sort of kind of okay?
I'm still trying to understand this one a little bit, to be honest.
It's sort of kind of okay, but maybe this will have to go on a formula sheet. Let's see.
Yeah. This is one of those things where like you have to be able to kind of see in 3D to get it without having to draw it out or like kind of memorize it. But it's not something that like if you don't see it, you can't get it right on the exam. No, this is one of those things that you can memorize and get away with it. It's not going to be a huge problem.
Yay.
Yeah, yay.
Yeah.
All right, so let's zoom back up to number.
After Kareem's question, could you do chapter 14 with the naming?
Yes, yes, we can. Number 4. Okay, for this one,
The answer was
yeah, we
equal
can.
amounts of 3 and 4, I think.
Yes, yes.
Okay.
So the reason for that is essentially this question is asking epoxidation, which is forming an epoxide, followed by reaction with base, converts this into what? So we're starting with cyclopentene. And we're reacting that with what to form an epoxide?
Alkyl halide? No.
That's Williamson Ether, but this is the other reaction.
Oh, inter Williston
Intra?
Ether?
No.
The
Is this
other
going to be
one,
like thermo or kinetic or something?
nope. This is the one that everyone forgets. Okay, so Williamson Ether is alcohol plus base and a alkyl halide. If we have a what do we call it? A double bond, we can only make an epoxide with a double bond by reacting it with O3, aka
peroxy.
peroxy acid.
Okay.
That's something that everybody always forgets about. So, yes, this had to be a peroxy acid in order to do the original epoxidation. And then now we're reacting this with base to open it up. So I'm going to try to draw this in 3D the way they have it. Or maybe I'll just mess it up. There we go. So we have our epoxide here, and this doesn't look as 3D as I wanted it to. Let me try doing it like that. Does this kind of look like it's going upwards? Like it's pointing up?
Yeah, it does.
Okay, cool. So we could either have the epoxide pointing up, or we could have it pointing down, which would be kind of like that. So if the epoxide is pointing up, Which side is the nucleophile going to attack from?
What is our nucleophile?
That was my next question.
Okay.
So aqueous base, what does that mean?
OH minus? I don't know.
Yes.
Okay.
So OH minus, and we're going to have water hanging out. Cool, cool. So if we react with OH, first of all, is there a preference for which side of this we're going to attack?
That's what I was trying to think about.
I was gonna say yes.
No,
Why not?
because they're both the same. Whether are they both primary? Let me check. So that carbon is connected to two other carbons, and that carbon is connected to two other carbons. So they're both secondary, right?
They're both secondary, exactly. So secondary, 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 secondary. So it doesn't matter which side they're going to attack in that respect, but it does matter whether they're going to come from the top or the bottom. So when the epoxide is pointing up, the nucleophile is going to come from the bottom. Bam. And if the epoxide is pointing down, this is going to come from the top. So I am going to copy and paste this because I don't want to redraw it. It's not going to come out as good. All right.
Rosemary?
Yes. What's up?
So does it matter which side you made the epoxide for this cyclopentene?
We're going to put a pin in that for 1 second.
Oh.
Because
Gets-
no, they didn't tell you anything about which direction it's pointing, and that's important. So that's why we did both ways. So since they didn't tell us if it's going up or down, wedged or dashed, whatever, we had to draw it out both ways. And now, in the example where the epoxide was pointing down, we're going to have an OH down here. And the new OH that just attacked has been added pointing up. The opposite is true for the one pointing up. So if the epoxide was going upwards, the OH from the epoxide is still pointing up. And the new group that we just added was added from the downward face. So it's pointing down. And as Anthony kind of alluded to, we had no idea which one of these we were working with. It didn't specify, so that means we had both in solution, which means both of these products are possible. So it could be up and down or up and down. The important thing to note is that they are opposite. So they must be trans to one another.
Rosemary.
Yes.
So like I was with you until like you started doing the OH and like which I understand is like the base. And then when you inputted the base, I understand like okay, so like you think you go with the carbon that's like primary or secondary, but it doesn't make a difference because they're both the same. So I get you put a OH on the outside, but um how come you throw another one in there? Like on each one? How come you put two OHs instead of one?
So, okay, great question. This OH comes from the epoxide.
Yeah.
All I did was protonate it. So that's this oxygen. And once we break open the epoxide, we protonate it and it turns into an OH. And then the black OH that's pointing down here and up here, that's what we attacked. So that's this guy.
So like when it comes to epoxides in general, you're just gonna usually make an alcohol, and then since we have a base that's like being inputted in this, then that alcohol, that OH from the base is just gonna be inputted into the
Exactly.
electrophile, right?
Yeah, so exactly. What's going to happen is we're going to always have at least one OH, like you said, and then the other OH could be any nucleophile that we have here. So if they give us a base, we add that. We get two OHs. If they gave us Br minus or an alcohol or something, then you would just add whatever group they give you.
Okay.
Okay.
So, Rosemary,
All right. Yes.
what is our nucleophile again?
Our nucleophile is going to be this guy with a negative charge, and this will be the electrophile.
Now, is it always an alcohol that attacks an epoxide?
It doesn't have to be an alcohol. It could essentially be anything with a negative charge. So it could be OCH3. It could be Br minus. It could be even be like we talked about earlier, a Grignard. So it could be a C minus, or I'll do just an order because that's
So, like a strong nucleophile.
exactly, yeah.
So, this is gonna sound dumb, but how do I remember all my nucleophiles that are strong?
Not a dumb question at all. In Orgo 1, they made you learn like what's a strong versus what's a weak nucleophile. For the purposes of this class, we can say that anything with a negative charge can act like a nucleophile. And that's going to be good enough to do this reaction. So anything with a negative charge. All right, and I'm going to go back and do the naming ones. I promise. Just give me 1 second. I will be right back.
What's up, Loda?
Hey, Anthony.
I haven't worked on a
Are
paper yet.
Hmm?
I was saying I haven't worked on a paper yet.
Oh, for like Orgo, for
Yeah.
Orgo Lab. Bro, I literally made the appointment for this literally right before like the it actually said I made this like an hour before this thing started, and it was just annoying because it's kind of like it said I can't do it because like it's like within an hour. The next thing I literally switched my time on my phone just so I can make a meeting to get into this.
You're smart.
Yeah, and
Okay,
I'm
that's
shocked it worked.
hilarious. And I was literally sitting here and I was like, how did this person sign up? I was like, how did they do that? You're not supposed to be able to do that. But
I
also
know.
that's a lot of work. So if that happens again, you can just email me and ask for the link. You don't have to do all that.
James
I
Bond, yeah.
mean, it's quicker.
No, for real.
I switch my time zone. They don't know where I am, so they're gonna be like, "Oh, okay, we'll let him in."
That's really funny. That is a lot of work. I sometimes you guys say things like that and I'm like, wow, you really must like me.
Yeah.
Or like
And
they
then
set
like,
yourself upstairs here. So
and then I literally knocked out, and right out as soon as I made it, and I woke up. I'm like, "Oh crap!" So I just tried to join
that's
as soon as I
hilarious.
can.
I really do feel that.
Yeah.
Our mascot is here. Ooh, he doesn't want to be here, so I'm gonna let him be, but they're chill. He didn't like that. Okay, so any last questions in this one before we switch gears? Because I did promise Anthony we could do a naming question from 14.
How do I know it was gonna be a proxy acid?
So the way we knew it was a proxy acid is because, excuse me, I had a hiccup. So cyclopentene. That means we had a cyclopentane with a negative, with a double bond, and that double bond only forms an epoxide when it's reacted with a peroxy acid. So that's how we knew that.
So if we ever get, okay, what if it was like a butene or like, something like that? Like, would they still all have like peroxy acid or would it be something else?
It will be peroxy acid. So anytime we have a double bond that's forming an epoxide, it was peroxy acid.
Okay, thank you. Write that down.
He has been sitting outside my door crying for like the past hour and a half. I finally let him in, and of course he complains and leaves. I
At
can't
least he
stand him.
shows he knows you care.
Yeah, he sometimes I feel like he just does that to just be like, huh, you're still my bitch. Okay. Which one did you want to do, Anthony? I'm guessing one of these ones. If they're okay, so he usually does put a couple naming questions and students struggle with it, but honestly, I think these are like the kind of fluff, easy questions. So let's just do randomly a couple of these. OMP. For a reference, I'll put what either any of those things mean. So let's say we have any group here. The position next door is ortho. Then we have meta. And then we have para. I think of it ortho. If you've ever heard of an orthological species in genetics, that means some species that evolve next to each other. So I think of next to each other. M, meta. This forms an M if you put something there. So it's meta. And then para, I think of the North and South Pole. So they're on opposite ends. That's how I remember those things. That might not be helpful to you, but okay, so nitro, fluoro, and they're meta to one another. So I'm going to do the nitro first. Nitro is NO2. And then meta to that would be right here. Fluoro is an F. So that's what this guy looks like.
Rosemary,
Now this one, yes, what's up?
I had to run to bathroom, but when Gladell was asking about cyclopentane and a peri acid, can we always assume that any cyclos will always use peroxide acids?
So it's not necessarily the fact that it was a cyclo, it was the fact that it was a pentene. So it was a double bond. So
Oh,
double bonds are always going to react with peroxy acids to form an epoxide.
okay. Thank you.
Regardless. Oh, sorry, Anthony.
You're good. You can go.
So like I understand what you said, Rosemary, but so that means regardless if it's cyclo or not?
Wait, the last part got cut off. Regardless if it's cyclo or what?
Not.
Yeah, exactly. So a double bond, no matter what it is, whether or not it's cyclo, has to be peroxy acid. So if we had this or this or this, all of those would still use peroxy acid because they're all double bonds.
Okay.
Okay. So para-bromoaniline. Aniline looks like this.
And
Nope,
then
yes,
H2.
NH2. And
And
then
then
para to that
P.
is opposite side. So it would look like this.
So like you think he's just gonna give us a few freebies on here that'll just be like, okay, name the structure?
Most likely. Yeah. At least two.
And then number 3 would just be like a benzene with like a OH sticking out as a substituent, and then you just put on the next line silane chlorine.
Yep.
Okay, I got this. Except 4.
Cool.
4 is a little weird.
4. Okay, yes, 4 is a little bit weird. So, benzoic acid. Benzoic acid is this guy.
Like a COOH, and then like the one, so 2 after that would be a methyl, and then like
Mm-hmm.
2 after that would be another methyl,
Yep.
right?
So we're gonna number it like this. Honestly, you could go either way around. It doesn't matter. I just like to go clockwise. So this is gonna be number 1 because it's the one with the priority group. And then number 3 and number 5 will have methyls on them.
Okay.
So if we were to use orthoparameta, what position are these methyls on?
In orthoparameta,
Mm-hmm.
which
That is
one?
meta. Number 3 is meta, and
They're
3
actually
is meta.
both meta.
They're both, yeah.
Oh,
They're
Yeah,
both
yeah, they all would be meta actually, yeah.
Yep. So this one is like the parent. So compared to that one, both of these are meta. Perfect. All right. So p-chlorobenzaldehyde. Benzaldehyde is exactly what it sounds like. It's a benzene with an aldehyde. And then para to that is a chloro, so it'll look like that.
Okay.
Okay. Number 6 is also a weird one because it's insinuating that the benzene is the side chain, not the parent chain. So let's draw a pentane. 1, 2, 3, 4, 5. 1 phenyl. So phenyl means it's directly attached. Oh, I made an oopsie. Hold on. I'm sorry. I messed
So
up the
would
whole
the
thing.
ending decide if it's so would the ending decide if it's a one what the parent chain is?
Yeah, exactly. So usually when we're naming whatever's all the way at the end, that's the parent chain. So basically here it's saying that the pentane takes priority and then the benzene ring is the substituent. And then that's going to be 1, 2, 3. So we have a methyl on number 3.
Oh, I would have gone that wrong. I'm from in my head. You said it's a parent chain, but in my head, I'm still gonna be like, oh, put it on the benzene.
Did you number
I
that
mean,
right?
What?
1, 2, 3, 4, 5. Nope. Wait. 1, 2, 3, 4, 5. Yes. 1 phenyl, 3 methyl.
Oh,
This should be right. Unless
Something
you
looks
switch.
off. Do it again.
I think you made it. I think you made a hexane instead of a pentane, because like I just counted that. That's 6 carbons.
Okay. Let's just erase it and do it one more time. So we have the benzene ring. And then coming off the benzene ring, we have 1, 2, 3, 4, 5. And then on carbon 3, we have a methyl.
Okay.
And what you were saying about like still being like, oh, it's the benzene is the parent, it doesn't really matter. I mean, it does obviously matter, but like for the questions you're going to get, it's either going to be a name and then you have to draw, or you have to pick the drawing, or it'll give you a drawing and ask for the name. And there won't be another answer that's like super close. As long as you know
Really
the
tries to trick
components,
you.
pentane, this is a methyl, this is a benzene, you can figure it out.
Okay.
It won't be anything like super, super duper close. But yes, okay. And then this one you won't have to do. Someone asked me this in tutoring earlier today, and this is like just a mean question.
Thank
He's
God.
not really gonna ask me. Yeah.
Uh,
This one too.
oh, that we don't do the 2, 11?
Yeah, 11 and 9 I wouldn't worry about. The rest of them are pretty good, like fair game questions. So, what do we think about this? There's a nitro and there's a methyl.
That would be meta 1, 3
Well, you don't
chloromethyl.
have to put 1, 3 actually because you put meta. So that implies that it's 1, 3. So you don't have to do both.
Okay, so it will be meta methyl aniline. Well, no,
Close.
that's
Okay, so
NO2.
that's NO2. So it's
Yeah,
actually going to be meta.
nitro or something.
There's two ways we could write this, and I'm honestly not sure which one he's looking for. You could either do meta nitro
Benzene.
toluene or meta methyl nitrobenzene. Because those are the two, like, this would be a nitrobenzene, this would be a toluene. So you can either say, this is a toluene that has a nitro group on it, or you could say this is a nitrobenzene that has a methyl on it. So does
So
it kind of make sense? Yes.
toluene is just a benzene that has a methyl on it, right?
Yep.
And will be classified as a phenyl that doesn't have an OH. Can there be a substituent on a benzene that is not a OH and still be considered a phenyl, or is it only OH?
Okay, so phenyl just means this. So it just means a benzene attached to something. A phenol is specifically a benzene ring with an alcohol. So when you're saying it out loud, they tend to sound really similar, but if you see it written, phenyl just means a benzene ring attached to something. Phenol specifically means this. It has to be an OH.
So then for phenyl, the first one, phenyl, yeah, it does sound close. So for phenyl, does it only have to be one substituent, or can it be more than one? Just to be considered a phenyl.
Okay, let me see if I understood this right. So if you have a chain that in chapter 13, I think, I told you that Dr. West considers 5 or more carbons to be like the parent chain. So 5 or more carbons beats the benzene ring. So if we have, let's say, this chain right here, and that chain has a benzene on it like this, we're going to say that this benzene is a substituent. So we're going to say this is a phenyl group because it's a benzene as a substituent.
Mm-hmm. Okay.
There doesn't have to be any other substituents here for it to be considered a phenyl. Yeah, if that's not what you meant, let me know and I'll think about it. But
I'm referring more to like what we see for number 7, because you see like how like there's like a CH3. If there's a CH3, that would be a toluene, but like that wouldn't be a phenyl, would it?
no, yeah, okay, so I get what you mean. So no, because in this case, the benzene ring itself is the parent, and there's 2 substituents on it. So we wouldn't call it a phenyl. We would just either use a common name such as toluene, or we would use benzene at the end to indicate that it's a benzene ring with something on it, not some kind of chain with a benzene ring on it. It's a
Okay.
super small distinction, but does that sort of kind of make sense?
Yeah.
Okay, good. All right, so for this one, let me actually check what he wanted the answer to be. Ha 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 ha, it's both. Okay, so it could have been either one.
I would have
Oh,
gone with
there's
the second one, honestly.
either one would be correct. So you could also say one. Wait, did it say one methyl? Yes. Okay. So I'll just put that for the sake of completeness. So it could have been any of these guys. Alrighty. And those are separate things. So this next one, there's two ways you should know this as well. So common name, what is that?
Is it isopropyl?
Isopropyl.
Yes. Okay. So isopropyl. Cool. So we could say that this is isopropyl benzene. Or, so I'll write it down, isopropyl benzene. Or we can say that this is a really stupid way that's probably going to confuse people, but you could say that it's 1-phenyl. Hold on. Let me just look at this before okay, cool. Never mind. Because he had some name for it last semester that really confused students, but he took that one out. So we could either say isopropyl benzene, or we could say this is an ethyl, and on carbon 1, we have a methyl. So 1-methyl ethyl benzene. This is still a confusing name, but do you sort of kind of see where I got those pieces from?
There's two carbons connected to an ethyl. There's my bad. There's like two carbons that are connected to a methyl.
Mm-hmm.
And then you just add a
Which
big
is,
benzene ring.
yeah. Which literally, that's just an isopropyl, so I don't know why they can't just use isopropyl, but sometimes they're annoying. So that means the same thing. And then yeah, I don't know why he puts things like this. I doubt that he's gonna have something like this. He might have 3 things on a ring, but it's usually gonna be 2 different things. Like it won't be a dianiline or whatever. But you could know the name for this one if you want to. I don't think it's a super good question. I think these 2 are better. And then these ones are really good.
I think that problem he got from the book.
Yeah, I think so too. This chapter has weirder questions than the rest of them. Like he doesn't put the same kind of practice problems, which I always find weird, but you know. All right, so I did run a little bit over. I hope you guys don't mind. I won't take up too much of your time though. So, any other questions before I let you go?
I came a little late, so like, is anything like before else you're gonna be posted or recorded or anything, or?
Yes, so I have been recording, and this is a very long recording, so I'm probably gonna have to post it as 2 separate parts. But I will, as soon as it uploads to my computer, I will upload it to YouTube for you guys.
So like, are all the things that have been recorded gonna be uploaded to YouTube, or are they gonna be uploaded to something else?
On YouTube, because Canvas is always weird and it doesn't properly upload things for me. So just in case you don't have the link, I shall send it to you. Yay, Kareem and I will be heard. Of course. Remember, you guys are the smart kids.
We're gonna be famous and all.
Yes. Dude, it makes me so happy when someone like subscribes to my channel, because I'm like, ha, I have 200 followers or subscribers or whatever. I'm like, I'm
I
famous.
saw like last year. Like when I was looking at your older videos, I'm like, oh wow, look at the beginning, like the whole Halloween theme.
Ah, yes. I love it so much. I didn't mean to press that. Yes, it makes me so happy. I'm probably gonna do that because I'm gonna make some concept concept videos for you guys. I got too excited. So I'm gonna put a new spooky intro in it. And yes, Leah also has a YouTube channel, and hers is really, really nice, and I love the
I'm
way
so
that
dead.
she organizes it.
Shout her out.
Yeah, she's so I love Leah. She's adorable. Yes.
So are you gonna upload this all these at once? Or like is it gonna be like one after another?
Okay. So YouTube likes to freak out on me sometimes. So I'm gonna try and post them in order. So I have 2 SI sessions I have to post, and then earlier's tutoring session, and then now's tutoring session. And I like to do them, I like to give it a little bit of space at least, just so they upload properly, because I've had sometimes where, like, if I put too many things to upload at the same time, it, like, doesn't load it properly, or sometimes it doesn't put audio or whatever. But they'll be around the same time. It won't be like I'll post one of them today and then one 2 days from now and then whatever. So I'll either do it tonight or tomorrow morning, and hopefully they'll all be up around the same time. You're very,
Okay.
very, very welcome. Heart.
Thank you.
You're very welcome. Nighty night. I almost said smiley face instead of just smiling, but okay. So I'll stick around for another minute if anyone has any questions, but have a wonderful night, and you're very welcome.